Well, hello and welcome back to part three of Gardening in a Changing Climate. If you'll remember in part one, we looked at the geological time scale, the definition of a mass extinction, the driver of mass extinctions, and then the first three of the five extinctions, the Ordovician, the Devonian, and of course the granddaddy, the Permian. In part three, we'll discuss the last two mass extinctions, the Triassic and the Cretaceous. We'll then look at how these mass extinctions compare to what is happening today. And then we'll look at some of the human influences. Before we actually start, I'd like to correct something I said in part two, namely that the collision of the subcontinents, Baltica and Appalachia, with North America was one of the instigators, the initiator of the Ordovician extinction. And it was not Baltica and Appalachia. It was actually Baltica and Avalonia, in case you care. And when I was scanning the screen, I saw the Appalachian Mountains chains, and I just jumped Baltica and Appalachia, but it's Baltica and Avalonia that combined, and those combined actually to form something called the Old Red Sandstone Continent, which I think we talked about in part one. The other thing I'd like to point out to you is that when I'm talking about these continents, North America, South America, Europe, Siberia, the continents I'm talking about then, it was not like North America was floating around with Mexico on the bottom, the United States, and then Canada. Okay, it didn't look like that. It didn't look anything like that at all. So what they do is they're comparing the rock formations that existed then to the rock formations that are in the continents now, and that's kind of how they figure out who was where at the time, but they did not look the same as they look now. So I just wanted to clarify that issue, if it was an issue for you. So then let's look at the fourth of the mass extinctions, 201 million years ago, and that was the end Triassic. The Triassic followed the Permian, and so at the beginning of the Triassic period, the Earth is just absolutely devastated. As we said, the Permian had just almost destroyed everything. Just a mass of dead stuff and fungus around, and I said it probably smelled pretty bad because of all the decay. The atmosphere was still very hot. Carbon dioxide levels are still very high. And that goes on into the early part of the Triassic. But eventually, life starts to return and refill the Earth. It's called the greening of Triassic Earth. As Earth recovered from this nearly total devastation of the end Permian. The climate, while still warm, the temperatures were falling from those 30 to 35 degrees Celsius temperatures down to a little bit more reasonable 22 degrees Celsius. Carbon dioxide likewise decreased from about 8,000 to whatever, 30,000 parts per million, whatever it was. It was down again to a more reasonable level of about 2,500 parts per million. Oxygen levels began to slowly rise again from that low of 10% that it had reached to a more oxygenated level of about 18% during the Jurassic period, which is the period that follows the Triassic. So the seas are filled again with fish, and on land, crocodiles reign supreme. Who knew? Crocodiles were actually in charge for a while. Dinosaurs are numerous, but they're pretty small. And early mammals, of course, were continuing their development. There were extensive reef systems that returned as well. That all ends very badly once again at the end of the Triassic with the end Triassic extinction, when altogether, once again, about 75% of all species become extinct, including most land plants and many fish. And that includes species that actually survive the Permian. Coral reefs become almost completely extinct and do not appear again in the record for about 300,000 years. It's the end of the reign of crocodiles and the beginning of the reign of dinosaurs. So what caused this thing? Well, once again, it's the usual suspect, carbon dioxide. There were huge injections of the gas into the atmosphere, which produced the usual effects, the warming of the oceans, the warming of the atmosphere, acidic and anoxic oceans as well. And the instigator of all this was the breakup of the supercontinent Pangaea, which began late in the Triassic period. Huge rift valleys formed and began to pull the continents apart. This starts again massive basaltic lava flows, which release volcanic gases, CO2 chiefly among them. The CO2 levels doubled from, again, around 2,000, 2,500 parts per million, somewhere in there, to about 4,000. And then they increased again to about 6,000 parts per million. Temperatures also spiked from around 22 up to about 28 degrees Celsius or so. And that all occurred in a very short period of time, perhaps as little as 1,000 years. So the extinction occurred over 4 relatively brief pulses, which extended over a period of about 600,000 years. And those pulses were probably related to the various phases of the breakup of Pangaea. The first phase was the most devastating and occurred in less than 22,000 years totally. Once again, those huge releases of carbon dioxide, followed by all those usual things. The seas become acidic, dissolved calcium carbonate then becomes the useless bicarbonate, which kills off the coral reefs, it kills off shellfish, and it destroys species that have exoskeletons, which is also much of the base of the food chain. And then you get starvation in the oceans and death there. The reef systems collapsed. And again, the base of the food chain just begins to just be destroyed. Today, we see, again, a rapid rise in atmospheric carbon dioxide, accompanied by global warming, ocean warming, acidification, and early signs of anoxia, as we have discussed. The deal about this is that, and I'll quote actually Peter Brannan in The Ends of the World. He says, the reefs of the Triassic were the first reefs similar to those of today. They were destroyed. The same would, and in fact is happening today. That's why it's such a really big deal. So let's move on then and find my slide changer here to about 66 million years ago. And during that time, if there was anyone around to look up into the sky, they would have seen a new star out there. And over the intervening days, perhaps weeks, that star gets bigger and bigger until finally it isn't a star, but it's an asteroid and it collides with the Earth. And this is the extinction that everyone knows about, the asteroid colliding with the Earth and destroying the dinosaurs. And prior to the extinction, dinosaurs did rule the Earth. After the extinction, though, mammals began their rise and eventually leading to us. But it wasn't just dinosaurs that died. Once again, about 75% of all land species become extinct. Plankton fossils, again, the base of the food chain, nearly vanished from the fossil record post-impact. So during the Cretaceous, Pangaea was in its final stages of breakup. The shuffling of the tectonic plates is spreading the seafloor apart and widening the oceans. And India is in the early stages of colliding with Asia. All of this is producing widespread volcanism and releasing carbon dioxide into the atmosphere, which again overwhelms the rock cycle and again produces the usual results. Carbon dioxide levels rose from around 1,500 parts per million, somewhere in there, up to around 2,200 parts per million. And temperatures followed, increasing up to around 20 to 22 degrees Celsius, somewhere in there, from the cooler Jurassic period. The polar regions were ice-free and covered by forest. There was little ice on Earth. Dinosaurs roamed Antarctica, for example. Let me again quote from Peter Brannan. With little or no ice and increasing size of mid-ocean ridges, sea levels were higher than at any time in Earth's history, rising from 330 to about 660 feet higher than today in the early Cretaceous, and then from 660 to perhaps as high as 820 feet higher than they are today by the end of the Cretaceous. The result then was vast, and that's the end of quote there. The result was vast, shallow seas covering most of the continents. In fact, land coverage of Earth's surface was only about 18% at that point, compared with today's 28%. So what caused it? Well, there are two competing theories, the most popular being, of course, the asteroid strike, which everyone knows about. Um, However, a second theory relates the extinction to massive volcanism in India, which produced huge continental basaltic flows. They're called the Deccan traps, and they're very, very similar to what we saw in the Permian with the Siberian traps, although they weren't not as extensive. Today, scientific theory is going to the conclusion that it was actually a combination of these two things. The asteroid strike set the whole thing off, and then the Deccan traps finished it off. So the Deccan traps had already started erupting before the asteroid struck. In fact, they occurred in two phases. The first and the smallest occurred before the asteroid. The second and most massive occurred about 100,000 years post-impact. Just prior to and during the asteroid strike, the Deccan traps were actually silent and were not doing much of anything. The impact of the asteroid strike rung, I've heard this, the comment or the thing, rung the earth like a bell, okay, causing magnitude 9 earthquakes all over the earth. And in fact, there are even projections that it may have been as high as magnitude 12 earthquakes. Now, if you're familiar with the earthquake scale, you know that a magnitude 6 is 10 times more powerful than a magnitude 5. A magnitude 7 is 10 times more powerful than a magnitude 6, and so on up the scale. So a magnitude 10, 10 times more powerful than a 9, an 11, 10 times more powerful than a 10, and a 12, 10 times more powerful than 11. You can just imagine that, you know, the strongest earthquake we've had on the earth recently is about a 9.1 or 2, I think, and that was a couple of years ago, where off the coast of Japan, creating that massive earthquake or massive tidal wave, which destroyed most of the villages along the east coast of northern Japan, and of course wiped out the Fukushima nuclear power plants as well. That was a magnitude 9, roughly. You can just imagine what a magnitude 12 would have done on the earth. So this huge shaking then mobilized a great big mass of magma, which is still lying below the Deccan traps. And testing shows that it takes about 100,000 years for newly mobilized magma to reach the surface and start a new eruption. In other words, to re-energize the traps. So then this is how it may have played out. So a 6-mile wide asteroid strikes the Earth near today's Yucatan Peninsula, and it doesn't actually strike the sea surface. The plunging asteroid has a huge pressure wave out in front of it, which pushes the sea surface aside. So the asteroid actually strikes the seabed below, and it punches it blasts a crater 110 miles wide in diameter, and it punches 20 miles deep into the mantle. The impact releases the equivalent of 100 million megatons of TNT. Now, if you want to compare that to something, the largest nuclear explosion that we have ever generated here on Earth, 50 megatons. And the devastation that caused we think that was massive. Can you imagine something that was 100 million megatons? The blast and thermal effects kill virtually everything, if not everything, for hundreds of miles around where the strike occurred. The seismic shockwave penetrated through the Earth, re-energizing the Deccan traps and causing much of the U.S. eastern seaboard to collapse and slide into the Atlantic. Huge volumes of aerosols then are thrown into the stratosphere, darkening the sun for months. Kind of like a replay of the Permian extinction, where we have, again, carbon dioxide, hydrogen sulfide, sulfuric acid, particulate debris, water vapor. All this stuff is thrown up into the atmosphere and forms this cloud mass over the entire Earth. Surface temperatures plunged by 14 to 18 degrees Fahrenheit on a global scale, but over land, it's estimated they fell by as much as 18 to 29 degrees. Again, we have nuclear winter. The cold kills tropical vegetation. Many of the animal species go extinct. The dark retards photosynthesis, which again kills off the food chain both on the ocean and on the land. So, I mean, again, we're getting kind of a replay here. The re-energized Deccan traps then, well, first of all, that clears up. The nuclear winter clears up. You know, we got 100,000 years between the strike and the Deccan traps. So it clears. Things are starting to get back to pretty much to normal and looking good. And then boom, 100,000 years later, the Deccan traps spring back into life, and we get a replay again of the carbon dioxide, the water vapor, all that stuff back into the atmosphere. Probably a replay of nuclear winter, although probably relatively brief. And then when that clears up, we've got tons of carbon dioxide in the atmosphere. The carbon dioxide has already acidified the ocean. So now the ocean and the atmosphere is warm from all that carbon dioxide, and the extinction continues. So what were the consequences of that? Well, obviously, one consequence was 75% of species become extinct. The extinction also brought an end to the 136 million reign of the dinosaurs, and ushered in the rise of mammals, and eventually us. So what are the parallels for today? Well, again, we have massive carbon dioxide releases, just as we did then, and in at least the 3 previous mass extinctions, which led to global warming, ocean acidification, and anoxia in the oceans. So in other words, not much has changed. So let's move on then to our next section, which is comparing mass extinctions to today. And the first thing I'd like to do here is talk about the deadly chain of events. And this is my creation, so you agree with it or not, but this is kind of what I perceive as happens to cause a mass extinction. And especially the last 3 mass extinction, because remember the first 2 were actually too little carbon dioxide, and here we're talking about too much. Okay, so the sequence is not necessarily serial. That is, one event follows the next event, follows the next event. We have to finish number 1 before we can do number 2, before we can do number 3. It's not necessarily that way. Some of them may, in fact, overlap, and probably most of the time do overlap. So initially, some mechanism, and usually again it's volcanism, produces a rise in atmospheric carbon dioxide levels. If they rise quickly enough, as we have seen, they overwhelm the rock cycle and the ability to check that rise, and they also the ability of animal and plant life to adapt quickly enough, and that kicks things off. High and rising carbon dioxide levels produce warming of the atmosphere. At first, much of that heat and carbon dioxide are absorbed by the ocean, warming the ocean and reducing the magnitude of atmospheric warming, at least for a short period of time. The oceans rapidly warm and acidify. And in fact, to digress just a little bit, recent research seems to show that once ocean temperature increases by more than about 10 degrees Celsius, dissolved oxygen in the water rapidly begins to decrease. Why? They don't know. More research to try to figure that out. But that low, if those oxygen levels in the ocean fall far enough, then it begins to suffocate species. Acidification then kills most of the smaller organisms that form the basis of the food chain, resulting in further die-off. Once the ocean is saturated with carbon dioxide and the limit of force to absorb it has been reached, then the atmospheric concentration of carbon dioxide begins to rise even more rapidly, producing even more heating and more warmth. High atmospheric temperatures lead to increasing rainfall, which combines with carbon dioxide to produce acid rain. The rain dissolves the nutrients. Remember, again, the weathering of the rock we talked about, and sends some of those into the oceans. This causes massive algae blooms, which again begins to consume even more oxygen from the ocean water as those blooms begin to die and decay. So now you have not only warmer water, but you've also got the combination of organic decay, and this if it's more than 10 degrees Celsius, apparently this also reduction of oxygen in the water. So we have anoxia. Rising temperatures on land and the disruption of the food chain then cause extinction of land species as well. Melting glaciers pour fresh water into the ocean, disrupting currents and producing stratification, which once again intensifies anoxic conditions and in fact probably extends them down into the deeper ocean water. So there you have it. That's kind of how I see things playing out and how they played out during the last 3 mass extinctions. So again, previous slide, we saw the chain of events that led to these last 3 extinctions. So, and we've also discussed those distinctions and we've seen how some of the factors causing them parallel conditions that are occurring today. This slide puts all those occurrences onto a spreadsheet, so I think it's a little easier for you to see them. I've also included the first 2 extinctions because some of the things that occurred then do mirror things that are happening today. So the left hand then starts with the Ordovician extinction and goes right down through the Cretaceous, with the bottom being today. And across the top then are the conditions that may have existed during that time: high carbon dioxide, low carbon dioxide, warming of the atmosphere, warming of the oceans, etc. across the top. I hope you can read across the top of there on that slide. So just because there's not an X in some of the boxes does not necessarily mean that that phenomenon did not occur. It may have been only a minor factor, or it simply just was not present in the fossil or the chemical record, so we really can't say whether it did or did not. So only things there that we can pretty much say happened are X's there. So I hope you're scanning this and seeing some really disturbing similarities. And I guess my question to you would be then, do you think there's enough similarity between today and past extinctions, particularly the last 3, to stir some serious thinking about what is occurring today, if not outright great concern? So what about today then? Well, as you can see there, Earth is experiencing changes not seen for hundreds of millions of years. And this slide shows some of those changes. And we're going to look at those changes as we go along here in greater detail to try to understand the magnitude of the problem that we have created and where it is going. Remember, in order to know where you're going, you got to know where you've been. Well, we just figured out where we've been. Now we're going to try to check out where we're going if we keep it up. So, I'm clearing my throat because I'm full of smoke. I'm sorry. We're recording this for people who may or may not know during the big fire events that were occurring in the Northern California, and so the sky is overcast and gray and covered with smoke, kind of like the nuclear winter, I guess. So atmospheric carbon dioxide levels then remained fairly constant over the past 800,000 to about 1 million years, fluctuating between about 200 parts per million up to around perhaps 300 parts per million during 200 parts per million during ice ages and up to about maybe 300 parts per million during the warm interglacial periods. Note the horizontal line on the chart where it says for 800,000 years, atmospheric carbon dioxide has never been above this line until now. And then you look down there at 320,000 years and you see it goes up above that line. That's our bad. When we did the slide, we had to put the line in separately, and we put the line and we got a little too low. So instead of redoing the entire slide, we just said, I'll explain it. So that line actually just touches the top of that 320,000 years. So it really didn't go above. So today we are experiencing a rapid rise in carbon dioxide concentrations, obviously. At the beginning of the Industrial Revolution, as we've said, carbon dioxide was about 270 to 280 parts per million. As of May 2019, as we've also said, it was about 415.226 parts per million, somewhere in there. And by May of 2020, it was actually up to just a tad under 417 parts per million. That's the highest it's been in 3 million years in the middle of the Pliocene. And that's when sea levels were 50 feet higher than today. And as we said before, the increase from May of 2018 to May of 2019 was about 3.75 parts per million, and the average increase over the previous decades was only about 2.5. And we also said that from May of 2019 to 2020, the increase actually decreased because of the reduction of carbon dioxide being put into the atmosphere because of the pandemic. So carbon dioxide levels then have risen by about 48% since the Industrial Revolution, and by about 26% over the past 50 years. Or put another way, it took about 200 years to raise carbon dioxide levels by 14%, but only 50 years to raise them by another 34%. So talked about that. So let's go on. So that rate of increase has been increasing over the years, except for the anomaly of this past year. At the current rate of carbon dioxide concentration increase, then levels will reach 540 parts per million, or double the pre-industrial revolution levels by about 2054. And that might be plus or minus 2 or 3 years, but roughly about that time. And this is going to cause a 3 degrees Celsius temperature rise. If you want to know your impact on atmospheric carbon dioxide concentrations, just consider this. 1/3 of the carbon dioxide you place in the atmosphere today will still be there 1,000 years from now. So you're probably viewing this sometime in September of 2020. So if you go outside right after you're viewing this, don't go out in the middle of it, go out afterwards, and you put 99 pounds of carbon dioxide into the atmosphere, okay, by the year 3000, September of 3020, 33 pounds of that carbon dioxide are still going to be up in the atmosphere. Today, humanity emits somewhere between 50 and 100 times the carbon dioxide of all the volcanoes on the Earth combined on an annual basis. Do you think the rock cycle can keep up with that, even aided by ocean and tree absorption? If in fact we are adding carbon dioxide to the atmosphere at a rate that is 10 times faster than the rate that led to the Permian extinction. It's just that the Permian extinction extended over about 10,000 years, and we're doing it a heck of a lot faster than that. We're doing it in a few hundred years, if even that long. The International Panel on Climate Change states that if we proceed with business as usual, carbon dioxide emissions, atmospheric temperature, with business as usual carbon dioxide emissions, atmospheric temperatures will rise by about 5 degrees Celsius by 2100. Now we're trying to keep carbon dioxide levels from increasing by more than 2 degrees Celsius by the end of 2100, and the desired increase is no more than 1.5 degrees Celsius. This projects they'll increase by 5. Compare that to the 3 to 6 degrees Celsius rise during the end Triassic extinction. Okay, so, and I'd also like to draw your attention then to the right side of the chart, which is the rate of increase and where we are today compared to where that whole thing over the past 800,000 years is showing we were. That's pretty drastic. In fact, we're off the chart. All right, to move on then. So I'll discuss the chart itself, the graph itself here in just a moment, but you can read a lot of the information I'm going to put kind of abbreviated over here on the right-hand side of the chart, but I'll go over some of that anyway. So obviously atmospheric temperatures are rising. That's kind of obvious. We've talked about it a lot, certainly. 18 of the past 19 warmest years on record have occurred since 2001. 2018 was the fourth warmest year on record since record keeping began, which was in 1880. The 3 hottest years since then were 2015, 2016, and 2017. and the warmest 5 years on record all occurred in the last 5 years. June 2019 was the hottest June since record keeping began, and it averaged about 60.6 degrees Fahrenheit. Remember, that's a global average temperature, or about 1.7 degrees Fahrenheit warmer than the 20th century average. 1.7 degrees Fahrenheit is almost 1 degree Celsius. 1 degree Celsius would be 1.8 degrees Fahrenheit. So remember that 2 degrees centigrade temperature limitation? Well, 1.7 degrees Fahrenheit is 1 degree Celsius for all practical purposes. So we're kind of getting there. June 2019 was followed by July, which became the new hottest month on record, with global temperatures averaging 62.13 degrees Fahrenheit, which is again about 1.7 degrees Fahrenheit above the 20th century average. 9 of the 10 hottest Julys on record have occurred since 2005, the last 5 being the hottest ever. July 2019 was the 415th consecutive month with above average global temperatures and was the 43rd consecutive month, or July, above the 20th century average. 2019 was the USA's wettest year on wettest on record for a July, for a year. And why do you suppose that would be? Could it be that warmer air holds more water, so we get more rain? Might be. What does that portend for the future with rising sea levels? So let's, a couple other little tidbits here. January 2020 was the hottest January in recorded history and the 44th consecutive January above the 20th century average and the 421st consecutive month with temperatures above the 20th century average. Actually, January's average temperature worldwide was 55.65 degrees Fahrenheit, which is 2.05 degrees Fahrenheit above the 20th century average. So, and 2.05 would be about, let's see, 1.15 degrees Celsius. So we're gradually closing in on that 1.5 degrees Celsius or 2 degrees Celsius rise that we're trying to avoid desperately. From 1910 to 2019, temperatures have increased. We're increasing at about 0.17 degrees Celsius per decade. But from 1980 to the present, that increase had doubled to 0.35 degrees Celsius per decade. So yes, temperatures are warming, and the warming is increasing at an ever increasing rate. The thing about it is that doubling atmospheric carbon dioxide produces a 3 degree Celsius temperature rise on a global scale. And that is regardless of whether the doubling occurs from 2,000 to 4,000 degrees parts per million, or from 270 to 540 parts per million. This slide then shows where we are today and how much the temperature will increase every time we double carbon dioxide levels. So the vertical scale then is the concentration of carbon dioxide in the atmosphere, and the horizontal scale is just the temperature in degrees Celsius. I hope you can see this. If you could look down that first arrow, I mean, we start at 270 parts per million because that's where we care about where we started pre-industrial revolution to where we are now. So if you look at that, we are up. The arrow shows you where we are now, and I sure hope you can read that. Actually, we're a little higher because this was put in before the latest increases, so it's around 417 parts per million now. Now, if we double carbon dioxide levels then to 540 parts per million, and we're well on the road to do that, it looks like we will do it then by about 2054, then you can see where we're going to be, and that's going to produce a temperature increase of about 3 degrees Celsius. If we continue putting carbon dioxide into the atmosphere at our current rate, then we will reach about 712, 713 parts per million. That's the top dot with the arrow on it by the end of this by the end of the century. Sorry, and that will you can see what that's going to do. That will produce a temperature rise of somewhere around 4.5 parts per million, which is right on track with what was projected. So Earth's average temperature then was 14.9 degrees Celsius in 2017. That was rising, and that 14.9 degrees Celsius compares with 13 degrees Celsius prior to the Industrial Revolution. Okay, so I'm going to quote again from Peter Brennan, because I quote him a lot because he just says it so much better than I can. Okay, so what he says is, quote, "Civilization has shown that volcanoes are not the only way to get carbon buried in rocks into the atmosphere. Today, we are digging up hundreds of millions of years of carbon safely buried by ancient life and igniting it all at once in the factories, vehicles, and power plants of modern civilization, and then injecting it all into the atmosphere. If we burn it all, it's going to get very hot, as it has before. Maybe we don't even have to burn it all. If this happens, the planet will return to a condition that has appeared many times in the fossil record. In fact, to conditions not seen since the Eocene epoch, which was 34 to 56 million years ago. Warm times are not necessarily bad times, or a bad thing. Just dinosaurs lived on a much warmer planet with higher carbon dioxide levels. The problem arises, my injection, as we've seen before, back to the quote, "When climate or ocean chemistry changes are sudden, not allowing time for life to adjust. That has been devastating to life," end quote. Such rapid changes are occurring today. And if nothing is done to reduce or steady emissions, temperatures will continue to increase, and probably increasing at an ever increasing rate. It doesn't seem much is going to change, because as world population increases, the demand for energy will increase with it. And as more of the world's population moves into the middle class, which it is doing, the middle class also demands more energy than poorer classes. Despite accords signed to reduce coal consumption, witness what is actually happening today. Coal shows no signs of disappearing. It's cheap, it's plentiful, and unfortunately, it's the most polluting of all the fossil fuels. It's the single largest source of energy to produce electricity worldwide. Asia accounts for more than 3/4 of the coal plants either under construction or in the planning stages, about 1,200 of them. What that means is, even if the United States decommissioned every coal-fired generating plant in the country, and we probably throw in Canada's too, whatever they've got, it wouldn't even make a dent in what the carbon dioxide emissions that are going to occur if all those 1,200 coal-fired generation plants are built. Indonesia is digging more coal, not less. Vietnam is clearing grounds for new coal-fired power plants, as is Japan. Wait, what a minute, Japan? Japan was going to go all nuclear in their electric generation and get rid of fossil fuel powered electric generation plants. Well, we had that little earthquake, remember that, a couple of years ago, which wiped out the Fukushima nuclear plants, and it really put a scare into the Japanese because of that. They went critical. So the Japanese reconsidered and decided now they're going to put a hiatus on new nuclear plants, but they've got to replace the generation capacity not only from the 4 reactors at Fukushima, but for the rising demand for electricity, even over and above that. So what are they going to do? They're starting to build more coal-fired generating plants. China has added 40% of the world's coal capacity since 2002 and is scrambling to find new markets. Why? Because remember those pictures of Chinese cities with the people before the virus, okay, wearing the masks, and the pollution, the smog is so bad you can barely see the hand in front of your face. That people were beginning to worry, of lung problems, of sickness, and everything else caused by this massive pollution. And they began to really voice those concerns. If there's one thing the Chinese Communist government fears, it's not the United States. It's not our nuclear weapons. It's not our military. It's not even our competition economically. It's if the population becomes unsettled and revolts, throwing them out of power. That's what they care about. And so they, seeing this happening, began to take actions to reduce the pollution. They went into massive production of solar cells. They lead the world now in solar cell production. They went into wind farms, and they also went into massive battery research and how to create better batteries that store more energy. In fact, they lead the world in that too now. And what that did is it began to slowly reduce the pollution levels in China, which was the goal. But what do you do with all that coal you got mined? Well, you got what they did is they went out into the developing world, into the developing countries, about 17 of them, and which all are having increasing demand for electricity, and said, hey, we're going to build you some nice coal-fired nuclear or coal-fired generating plants there to fill your electricity needs. Of course, incidentally, that creates a market for all that coal they've got. Mm-hmm. So they've reduced the carbon dioxide emissions in their own country, or at least they've kind of reduced the amount of increase of them. But they're now having an increase of carbon dioxide emissions from all those coal-fired plants over here in these other countries. Well, folks, it doesn't matter who puts the carbon dioxide into the atmosphere ultimately. It spreads around and fills the entire atmosphere. So what you're really getting here is not much of a reduction at all. Okay. India is producing more coal every year also. Again, rising population and more of the population moving into the middle class. In the Arctic, where melting sea ice is opening the ocean bottom to mineral and hydrocarbon exploration, the countries bordering the Arctic are running all over themselves to claim portions of the seafloor. So yes, they can prospect for minerals, but also so they can pump the hydrocarbons that are down below the seabed. Well, let's see now. The sea ice is melting because we put a lot of carbon dioxide into the atmosphere, which is warming the atmosphere, which is causing the sea ice to melt so that they can get to the ocean bottom, so that they can pump more hydrocarbons so that we can burn them and put more carbon dioxide into the atmosphere. What's wrong with this picture? There we go. So these combination of graphs here show the concentration of carbon dioxide in the atmosphere, average temperature, and sea level changes over the past 420,000 years. Note the close correlation between carbon dioxide concentration and the rise and fall of temperature and sea level. They're virtually moving in lockstep. Would that suggest anything to you? The periods between ice ages are called interglacial periods, and there have actually been about 50 interglacial periods over the past few million years since the end of the Eocene, which is about 34 million years ago. The entire period from the end of the Eocene to the present has been a period of a relatively cool, stable Earth with carbon dioxide levels again fluctuating within that narrow range of about 200 to 300 parts per million. Those interglacial periods don't usually last very long, a few thousand to perhaps 10,000 years before the ice returns. With carbon dioxide fluctuating within this narrow range, the Earth's wobble on its axis and the rhythmic changes in its orbit contribute to glacial and interglacial patterns, which we've discussed before. Remember the Milankovitch cycles? Okay, that's what it is. To quote Peter Brannan again, we are technically still in an ice age, just in one of the warm interglacial periods. However, our few interglacial years are about up, and if the pattern were to continue, we should be entering the next ice age and deep freeze of the Pleistocene for another 100,000 years. But because of the ways humans have altered the chemistry of Earth's atmosphere and oceans over the past 250 years, this regularly scheduled ice age has probably been postponed. And it's not getting cooler anytime soon. End of quote. Note the right end of the graph of the carbon dioxide concentration graph. which mirrors the one we saw before. Okay, so during the interglacial event about 120,000 years ago, known as the MEN, and you can see that, I think it's on the middle graph there, temperature was a few degrees warmer than present day, and sea level was about 26 feet higher than today. With our present pace of warming and the fact it's happening much faster than previous periods, that higher sea level has a major concern should it happen again, because of the major coastal flooding that it would produce. Again, the biggest concern is obviously the rising carbon dioxide levels. Again, look at that right side of the graph. We've noted that carbon dioxide has risen by 48% since the Industrial Revolution. That correlates almost like this graph, almost perfect correlation. Well, that correlates with the burning of fossil fuels and the reduction of forest cover. In fact, the reduction of forest cover increased by 13% from 2017 to 2018. If temperatures continue to rise this century, and there's no reason to think that they won't, given the steady rise in carbon dioxide levels, which are causing ice sheets to melt, there will be even greater problems. The last time carbon dioxide levels were near 1,000 parts per million was about 55 million years ago in the Eocene. And at that time, there were no polar ice caps, and sea level was about 250 feet higher than it is today. Kind of where we're headed, maybe, huh? While sea level and climate change in the past changed often in the past, and sometimes quite drastically, it was long before human civilization. The effect of such a rise today could be draconian. Once that ice melts and sea level rises, there is no way to reverse the process quickly. So let's look at those warming and acidifying seas. Right now, the oceans are absorbing much of the heat generated by atmospheric carbon dioxide. In fact, they've absorbed about 93% of the heat we put into the atmosphere. That has moderated atmospheric warming to some degree, but at the expense of ocean warming. The world's oceans hit their warmest level in recorded history in 2019, and it was that was not only the warmest year on record, but also was the largest single increase in the entire decade. The pace of warming increased by 500% since 1980. In fact, the rate of ocean warming accelerated from 1987 to 2019 to nearly 4 to 5 times the rate of warming from 1955 to 1986. As we've seen then, recent studies indicate that when the oceans warm by more than about 10 degrees Celsius, dissolved oxygen rapidly leaves the ocean for whatever reason. And that can lead then to anoxic conditions if it falls far enough, and the death of marine species. Oceanic warming alone then can be fatal to species, particularly coral. The primary effect is coral bleaching, and waves of bleaching events are unprecedented over the past several thousand years. In fact, it has become quite common, and we'll discuss it in more detail a little bit later on. Oceans also absorb carbon dioxide, which is again has moderated warming, but the ability of the oceans to absorb, and forests to absorb carbon dioxide may be reaching about a limit. There are indications right now that we're approaching that limit. So if that would happen then, the limit reached, well, then more carbon dioxide remains in the atmosphere, which just accelerates warming and makes the problem even worse. Oceanic carbon dioxide absorption also comes at a price, and that price, as we have seen, is acidification. And this leads then to reef destruction, as well as disruption of the food chain, leading to further species loss. And we'll discuss that again in a little more detail a little bit later. Today, reefs have decreased by 30% since 1980. Coral growth rates have decreased by 20% in the last 20 years. The combination of warming and acidification then is wreaking havoc on the reef system. And we'll see why that's important a little later also. There have been recent studies that show that coral has the ability to move from warmer waters where it's not surviving well to cooler waters in response to this warming of their native seas. Well, you know, okay, if they can do that and if they can do it quick enough, that certainly would help to solve the warming problem. But it doesn't do anything for the acidification problem. So reefs are still going to be in trouble, even if they are able to move to cooler waters. So let's move on then to human influences. It's a part 5 of in our outline. And we'll look first then at a combination of the mid-latitude deforestation and rainforest deforestation. So both mid-latitude deforestation and rainforest deforestation remove huge carbon sinks from the earth. The trees soak up large quantities of carbon dioxide. In fact, on average, each tree soaks up about 48 pounds of carbon dioxide per year, removing it from the atmosphere and safely sequestering it, at least for a time, within the tree. Forest destruction also removes habitat, leading to reduction of speciation, and it contributes to erosion, washing the nutrients into the sea, and then, well, we know what that does. We've talked about it a lot. Rainforests are also lost to slash and burn agriculture. The burning adds vast quantities of carbon dioxide to the atmosphere. So burning trees has a double whammy. It removes a major carbon dioxide removing system from the plant, that is the trees, and the burning of those trees adds carbon dioxide into the atmosphere. Remember that 13% increase in forest acreage loss from 2017 to 2018? Well, that acreage loss has just increased from 2018 to 19 and probably will again in 2019 to 2020. In Brazil, the newly elected president, well, he was actually elected 2 years ago. When I wrote this, he was newly elected, is a pro-growth climate change denier. He's reversed years of laws and restrictions that slowed the destruction of the Amazon rainforest. It's now open season on the Amazon. The problem is forest destruction creates a feedback loop, right? That reduces rainfall, makes it more sporadic, and results in an ever-increasing number of droughts, all of which are happening now in the Amazon. And it also causes temperatures to rise further, which just worsens the problem. In fact, trees have absorbed about 25% of the carbon dioxide we put into the atmosphere, and combined with the ocean, they've actually removed oceans and trees about 50% of the carbon dioxide we put into the atmosphere. Studies show that if deforestation continues, the Amazon may reach something called a tipping point, and it's not far in the future where the entire ecosystem collapses. What do you suppose that'll do for global warming? So again, burning the forest adds carbon dioxide to the atmosphere while destroying a major carbon dioxide removing mechanism. To make matters worse, much of that forest is being cleared to make grazing lands for cattle. Now, cattle are enormously flatulent, and their flatulence is primarily methane. And methane is a much more powerful greenhouse gas than carbon dioxide. Is this insane or what? So, the Amazon is still critically important as it pulls carbon dioxide from the atmosphere, which helps to keep the earth cool. This makes it one of the most powerful agents in lessening climate change. It also stabilizes rainfall cycles in the Amazon and throughout South America. Its destruction then is just going to be bad news for all of us, not just for the people living down there. So let's look then at the Industrial Revolution and the rise of modern transportation. And we've talked about this Industrial Revolution, how the burning of fossil fuels puts carbon dioxide into the atmosphere. Well, the revolution ultimately led to the rise of the modern transportation system to transport all those goods, all the raw materials, and eventually people around the earth. All those trains, those trucks, those airplanes, those ships, they all burn fossil fuel and dump the carbon dioxide into the atmosphere, essentially using the atmosphere as a garbage can. transportation is one of the chief contributors of carbon dioxide to the atmosphere. That transportation system also leads to the loss of speciation, as non-native plants and animals are transported worldwide, leading to the destruction of native species and the resulting monocultures. And we talked about that before. How about burning of hydrocarbons? Well, I think we've kind of bashed that one in the head pretty good, but let's just recap just a little bit. The digging up and pumping of fossil fuels, burning them, takes carbon dioxide or carbon that was safely sequestered in the earth, burns it and dumps it, the resulting carbon dioxide back into the atmosphere, thus reversing an action that took hundreds of millions of years to make our atmosphere suitable for life, including ours. Something about the disruption of the nitrogen cycle. We've been talking about the disruption of the carbon cycle through the disruption of the rock cycle, but which again is a mechanism the Earth has to maintain carbon dioxide balance. And but we've also disrupted something called the nitrogen cycle, and that's through the development of chemical fertilizers. Until the 20th century, almost all biologically available nitrogen, which is essential for plant growth, right? You gardeners out there, you know that, was fixed in the soil by microbes. That limited the amount of food that could be produced, and therefore it limited the population growth. Development of synthesized fertilizers, developed from fossil fuels, by the way, produced an explosion of food production. It was called the Green Revolution, and it was cheered. Okay, it enabled rampant population growth. It also leads to this destruction of the soil biome and contributes to ocean destruction, and we'll see that next. It took 200,000 years, up to 1850, for world population to reach 1 billion people. Now we are adding an extra 10 billion people, or a billion people rather, every 10 years. This is putting an ever-increasing pressure on the Earth's biome, further reducing speciation and the ability of the atmosphere to rid itself of carbon dioxide. What about agricultural runoff? Well, once again, we've talked about that a lot, but again, excess agricultural fertilizer along with sediment from deforested areas washes into the oceans, sparking those massive algae blooms. The algae blooms can consume oxygen from the water as it dies and decomposes, which can lead to anoxic conditions and large dead zones, which we have seen, including the one off the Mississippi River, where we're putting massive amounts of agricultural runoff through the Mississippi River into the Gulf of Mexico. You gardeners can worsen that problem in your own garden, all right, by putting too much nitrogen down on your ground. So first of all, if some of that nitrogen, if it doesn't get used, it can run off into the streams, into the rivers, and into the oceans, and so on and so forth. Now, admittedly, your actions as an individual make zero consequences, but if you got hundreds of thousands of people doing this, that starts to add up. All right. So that's one problem with too much. Another problem is that if that nitrogen is not used, it can leach down into the groundwater and eventually into the aquifers, and that pollutes the aquifers with nitrogen compounds. That's what happened down in the southern San Joaquin County. Okay, this is not a computer projection. It actually happens, and it happened down there, where nitrogen compounds from the fertilizer put on the ground leached into the aquifers and contaminated those aquifers. That's why people down there now in these smaller towns, they can't pump their wells for domestic water use. They have to import it because it's contaminated. And to make matters worse, down there, that soil has a relatively high concentration of arsenic. The arsenic, with all that irrigation, was also dissolved and leached down into the aquifer. So you not only got bad nitrogen compounds, but you got arsenic in it too. Just not good, not at all. The other way you can mess things up is if you put too much nitrogen on your garden. That nitrogen does something called, if it sits there on the surface, it volatilizes. What's volatilizing? Well, it's just basically evaporation. So nitrogen compounds then are evaporated up into the atmosphere, again, putting bad nitrogen compounds into the atmosphere. So gardeners, take note, use nitrogen, use fertilizers responsibly, and we'll talk about that a little bit later on as well. What about the inverting of vertebrate life? Well, all that cultivation and livestock raising is inverting vertebrate life as well. Until recently, nearly all vertebrate life was wildlife. Today, only 3% of vertebrate life is wildlife. The other 97% is humans, our livestock, and our pets. The rest is gone due to hunting and habitat loss. The same destruction of animal life on land is now being visited on the ocean. About 90% of all large ocean predators have either disappeared or are in decline since 1950. The list includes, well, you guess what it is. It's the food fish: cod, halibut, grouper, tuna, swordfish, marlin, and yeah, sharks as well. The same goes for coral reefs. About a 33% decline since 1980. Modern reef systems are expected to collapse due to ocean warming and acidification by about 2100, if not sooner. Krill, the basis of the ocean food chain, is being depleted with up to a 70% decline expected in Antarctica by 2100. Do you remember what happened the last couple of times the ocean food chain collapsed? What about human-caused extinctions, the loss of speciation as it shows up on the slide? Well, we're causing the extinction of many plant and animal species, both directly, indirectly, as we've seen, and also directly through habitat and habitat destruction and through hunting. Large land vertebrates mostly survived alternating ages, ice ages, okay, and warm periods by simply moving to a more accommodating climate so they could survive changes. That is until humans appeared on the scene a few thousand years ago and began hunting them to extinction. And again, why the large vertebrates? It's the meat. So large land animal extinction traces a path of human migration from continent to continent, island to island. And it continues today on both land and in the ocean. So who cares? Well, besides the morality of it all, it's once again contributing to the loss of speciation of species and the corresponding decline in speciation. And again, we've talked about that. A recent census of life on Earth shows that humans are responsible for the extinction of 83% of wild mammals and 50% of plants that have become extinct. Humans now take up 50 to 70% of Earth's land surface, and the rest of it's mostly mountains and vertical stuff where the mountain goats might like it, but most else doesn't. Nature is in more trouble now than any time in human history, with extinctions looming over 1 million of the estimated 8 million species of plants and animals on Earth. And that includes about 10% of insects and about 25% of plants and animals. Humans are reducing biodiversification in several ways. In fact, I'll give you 5. So one is the destruction of forests and grasslands. About 3/4 of the Earth's land, 2/3 of its ocean, and 85% of crucial wetlands have been severely altered or totally destroyed, particularly wetlands totally destroyed. Overfishing, and that just obviously is causing habitat loss. Overfishing in the world's ocean is still another. Burning fossil fuels, making it too hot, too wet, too dry, or oceans too acid for species to survive. Polluting the land and water, and the spread of non-native species crowding out native species, leading to the homogenization of species and loss of speciation. At least 680 species with backbones have already gone extinct since 1600. More than 40% of amphibian species, more than 1/3 of marine mammals, and nearly 1/3 of sharks and fish are threatened with extinction today. So the question is, are we in a mass extinction now? And the answer is probably not. Remember, a mass extinction is when 50% of Earth species go extinct in less than 1 million years. Well, folks, we aren't even close. We got to step up our game. Okay, so all is not lost, right? Consider that over 400 years, we've only managed to kill off about 800 to 1,000 species, more or less, or about 1/10 of 1% of all species. Granted, most of what we haven't killed off is small stuff that we can't eat, or it's just so prolific that it's difficult to kill them all. I mean, really, previous mass extinctions have killed off nearly 100%. At our current rate, and I'll quote Peter Brennan again, at our current rate, it will take hundreds, if not thousands of years to reach extinction levels comparable to the big 5 extinctions, end quote. So cheer up. Be happy. Grab a 6-pack. Watch a football game. No need to worry at all. It's a long way off. Elephant's going to die anyway, right? Or maybe not. Remember that 1 million species of plants and animals are in danger of extinction in the coming decades, according to a report released in May 2019. That gets us up to about 12 to 13% of species. Helps. It's a gradual accumulation of environmental insults could move us to a tipping point. Okay. Unexpected surprises might accelerate the movement. Think collapsing ice sheets, melting ice caps, sudden release of methane from melting permafrost, or something else, you know? Why, if coral reefs collapse by 2100, as expected, we can get rid of 30 species all at one time. I'm going to quote Peter Brennan again. We might not even notice the change. The dinosaurs probably didn't, until we reach the tipping point when suddenly there are large biotic changes and things suddenly spiral quickly downhill. Mass extinctions are something like coming up on the event horizon of a black hole, if you're familiar with black holes. Everything is fine until you cross it. But once you do, there is no turning back. The tipping point has been reached. The same with mass extinctions. Everything is fine until it isn't. End of quote. So again, are we in a mass extinction today? Probably not. But if we keep doing what we are doing, we will get there. The definition of insanity, or at least one of the definitions of insanity, is to keep doing the same thing over and over again and expecting a different result. The Earth has already tried the carbon dioxide experiment several times and got the same result. What makes us think the result will be any different if we try it? Do we really have to engineer a 6th mass extinction? Here's the thing. We have time to prevent what is happening from becoming a mass extinction, possibly including us. We don't have to cause that 6th extinction. The question is, do we have the willpower and the intelligence to prevent it? And with that, then I'll leave you to ponder that for the next week. And this will close then part 3. I hope you've learned something from it. I know there's a lot of numbers there. I don't expect that you're going to remember all those numbers. I don't. I have to read them. You probably saw me. I was reading a lot of them. It's not the exact number that's important. It's what the trends are and what it means. That's what you really want to remember. So this wraps up part 3. I hope to see you back again for part 4. And in the meantime, thank you once again for the privilege of your time.